All right, let's start by talking about the notion of quantum advantage. Now, as we all know, quantum computers seem to be more powerful than classical computers. Perhaps the most famous example of this apparent advantage is given by the factoring problem, where by Peter Shor's landmark result, a quantum computer can factor an integer in polynomial time, whereas there's certainly no known classical polynomial time factoring algorithm. In this paper, we consider the quantum advantage question in a setting that's a bit different from the previously mentioned polynomial time setting. Namely, we restrict our attention to algorithms that are only allowed to use a small amount of space. Where here, small space, we mean sublogarithmic space, that is space little o log n, with a focus on the extreme case of constant space. Interestingly, in the small space setting, quantum computers provably outperform classical computers in terms of the amount of time they need to solve certain natural computational problems. In this paper, we present some new results about quantum advantage in the small space setting. But before discussing those results, let me first spend a minute trying to convince you that space actually matters in quantum computation. Now, the fact that we have these important problems, like factoring, for which there's an apparent quantum advantage, has provided excellent motivation for constructing real, physical, experimental quantum computers. And after several decades of progress, we've entered what John Preskill calls the noisy intermediate scale era of quantum computation, where here intermediate scale refers to the fact that these quantum computers have few qubits. For example, consider a current state-of-the-art quantum computer, IBM's Q system, which has 53 qubits. To put that number in perspective, we can compare this state-of-the-art quantum computer with a not at all state-of-the-art classical computer, Apple's iPhone 7, which has 128 gigabytes of memory and has a retail cost of something like $400. Now, I don't know exactly how much IBM's Q system cost to build. I imagine it's some sort of trade secret, but I think we can safely assume it's a great deal more than $400. Now, of course, this is a somewhat unfair comparison, as when one says the iPhone 7 has 128 gigabytes of memory, that is conflating together multiple different kinds of memory. But the basic message is true. Current and near-term quantum computers have few qubits. They have a small amount of quantum memory. And so space really is important in quantum computation. And if you believe that, it's natural to then ask, what is the power of a quantum computer with a small amount of space? Where here we'll focus on the extreme case of a quantum computer with a constant amount of space, which we'll model using finite automata. In particular, we consider the two-way quantum classical finite automaton, or 2QCFA, originally defined by Ambinas and Watrous, as follows. We start with a 2DFA, that is a two-way deterministic finite automaton, which consists of finite control, a read-only input tape, and a two-way head. And we augment this 2DFA with a quantum register of constant size. We allow the machine to interact with the quantum register however it likes. It can perform arbitrary unitary transformations and arbitrary quantum measurements, and it can use the results of those quantum measurements however it likes. Now, this is a standard model. I'm not going to spend any more time belaboring the details of the definition, but they are here on the slide, and so if you'd like to stare at the details for a moment, feel free to pause the video at this point. Continuing, in the same paper in which Ambinas and Watrous first defined this model, they also exhibited two examples of languages for which 2QCFA provably outperform classical finite automata. The first such example is the language LEQ, which consists of a run of zeros followed by an equivalent one of ones. As they showed, a 2QCFA can recognize this language with bounded error in order n to the fourth time. And in this paper, we improve that to n cubed time. Of course, one can't hope to do much better than this, as there is the trivial lower bound that a 2QCFA cannot recognize this language in little o n time. Now, as a 2QCFA is just a 2DFA plus a constant size quantum register, it's natural to compare this result with the old result that a 2DFA cannot recognize the language LEQ in any time bound. But to be fair, we also should compare a 2QCFA with a 2PFA, that is a two-way probabilistic finite automaton, which is simply a 2DFA that we've augmented with the ability to flip coins, as probabilistic computers are also classical computers. Now, it's known that a 2PFA actually can recognize the language LEQ in exponential time, but it needs exponential time. There's a matching lower bound. A 2PFA cannot recognize LEQ in sub-exponential time. And so this language really does demonstrate provable quantum advantage in the constant space setting. It's a language that a 2QCFA can recognize in polynomial time. A 2PFA can also recognize, but in exponential time, and it needs exponential time. In particular, it cannot recognize this language in polynomial time. And a 2DFA cannot recognize the language at all. The second example of provable quantum advantage considered by Ambinus and Watrous is the palindrome language, where, as they showed, a 2QCFA can recognize palindromes in exponential time, whereas it's known that a 2DFA and even a 2PFA cannot recognize this language in any time bound. And so again, this is an example of provable quantum advantages in the constant space setting. It's a language that 2QCFA can recognize in exponential time, but a 2PFA and 2DFA cannot recognize at all. But it's also natural to ask, can we do any better? That is, can we prove a lower bound? We know that a 2QCFA can recognize this language in exponential time, but could be recognized in sub-exponential time, perhaps even in polynomial time, as was the case for LEQ. In fact, is there any language that a 2QCFA can recognize in exponential time, but not in sub-exponential time, or at least not in polynomial time? These were all open questions, and in a separate paper, which builds on this one, we show that in fact you can't do any better than the Ambinus and Watrous 2QCFA construction. No 2QCFA can recognize the palindrome language in sub-exponential time. But here it's worth again emphasizing that this is the first example of a language that provably requires exponential time on a quantum finite automaton. Now, in order to prove the results I've already mentioned, as well as several other results, we study a particularly interesting sort of language, the word problem of a group, where while neither of the two previous example languages are group word problems, they are each closely related to a group word problem, and our results about those languages will follow, as special cases, of our more general results about group word problems. So let me first define what a group word problem is. For a finitely generated group G with finite generating set S, the word problem of G with respect to S is the collection of all strings over the generators and their inverses that represents the identity element of the group G. In other words, if we combine the sequence of elements using the group operation, we get the identity element. One little detail about the definition of this language, it does depend on the choice of generating set S. However, membership of the word problem in any reasonable complexity class will not depend on the particular choice of finite generating set. And so we're just going to write WG to denote the word problem of the group G. Now, what makes the word problem so interesting is that the computational complexity of the word problem of G is extremely closely linked to certain algebraic properties of the group G. And this correspondence is illustrated by a tremendous number of different results. I'm just going to state a few that are particularly interesting and relevant. First, there's Anismov's classification of those groups with regular word problem. In particular, the word problem of G is a regular language if and only if G is finite. We also have the classification due to Mueller and Schupp, who showed that the word problem of G is a context-free language if and only if the word problem of G is a deterministic context-free language if and only if G is virtually free. Where, just to remind you, the context-free languages are those languages recognizable by non-deterministic push-down automata, and the deterministic context-free languages are those languages recognizable by deterministic push-down automata. Now, what makes this second result interesting, in addition to being an exact classification, is that it might at first glance look a bit peculiar, as it's known that the deterministic context-free languages are a proper subset of the context-free languages. But what this result is really saying is that there's no word problem that witnesses that separation. In other words, non-determinism does allow push-down automata to recognize additional languages, but non-determinism does not allow push-down automata to recognize additional word problems. Now, I certainly wouldn't want you to think that results like this are only known for automata models, finite automata, push-down automata, and so on, because in fact, it's known that the word problem of G is in NP if and only if G is a subgroup of a finitely represented group with polynomial den function, where the exact property that G needs to have is not the terribly relevant point, and if you're not familiar with the terminology from group theory, that's quite all right. The key takeaway here is that this is an exact classification. The word problem of G is an NP if and only if G has a certain algebraic property. And the two previous results mentioned are also exact classifications of word problems in particular complexity classes. The last result which I'll mention is that if G is a linear group, then the word problem of G is in L, deterministic log space, where this last result is not an exact classification. If it were, that would provably separate NP from L. But I mention it because the technique that was used to show this result very much forms the launching point for the techniques used to show our result about those word problems recognizable by 2QCFA. Now, in order to state our results, we will need one somewhat messy definition. We define the complexity class B2QCFA TKF as the collection of languages recognizable by 2QCFA with two-sided bounded error in time at most t of n on inputs of length at most n, where the 2QCFA has a quantum register with k quantum basis states, in other words, approximately log k qubits, and all the transition amplitudes of this 2QCFA belong to the set F. We care about the transition amplitudes of a 2QCFA as it's known that using very complicated transition amplitudes, for example, non-computable transition amplitudes, allows a 2QCFA to recognize a very broad class of languages. But fundamentally, that power is coming from the unreasonable complexity of the transition amplitudes. It's not coming from the quantumness, and so we don't want to allow that. Now, we show several results. I'm just going to state a few of them. First, in this paper, we show that if G is virtually abelian, then the word problem of G is recognizable by a 2QCFA with bounded error in polynomial time, where that 2QCFA has a quantum register with only two quantum basis states. In other words, it's a 1-qubit machine, and the transition amplitudes of the 2QCFA are all algebraic numbers, so only simple transition amplitudes. That's our first result. We also show that if G is virtually UK, then WG, the word problem, is recognizable by a 2QCFA in exponential time, where now the 2QCFA has k quantum basis states, but the transition amplitudes are still algebraic numbers, so still simple transition amplitudes. Now, what makes these upper bounds interesting is that in a companion paper, we show the following lower bounds. Firstly, if the word problem of G is recognizable by a 2QCFA in polynomial time, then G is virtually nilpotent. Where here, the 2QCFA can have any constant number of quantum basis states and any transition amplitudes. Now, it should be noted that this is not an exactly matching lower bound. The virtually abelian groups are a proper subset of the virtually nilpotent groups, but it's a small gap. It's almost an exact classification of those group word problems recognizable in polynomial time by a 2QCFA. Now, in that same paper, we also show the following lower bound. If the word problem of G is recognizable by a 2QCFA in sub-exponential time, then G is either virtually nilpotent or of intermediate growth. And so by combining the upper bounds from this paper and the lower bounds from the companion paper, and by exploiting the fact that if a group G is virtually UK and either virtually nilpotent or of intermediate growth, then it's virtually abelian, we conclude that if G is virtually UK but not virtually abelian, then the word problem of G is recognized by a 2QCFA in exponential time, but not in sub-exponential time. And so these languages are examples, in fact, they're the first examples of languages that provably require exponential time on a quantum finite automata. Then, as an easy corollary, we obtain the lower bound that was stated earlier for the palindrome problem. Now, next, I'll explain the main idea behind the proof of the results from this paper, where the first thing we'll need is the definition of a representation of a group G, which is simply a group homomorphism, rho, from G into a general linear group, where GLKF is the group of all k by k invertible matrices over some field F. And just to remind you, a group homomorphism is a map that respects the group operation. In other words, applying rho to the product of two group elements is the same as applying rho to each of those group elements individually and then taking the matrix product. We say that the representation rho is faithful if the only group element that rho takes to the identity matrix is the identity element of the group. For example, F2, the free group on two generators, A and B, has the following faithful representation, rho, which takes the generator A to the matrix 1, 2, 0, 1, and the generator B to the matrix 1, 0, 2, 1. Of course, as rho is a homomorphism, as soon as you define the value of rho on the generators, you define the value of rho on the entire group. And so rho takes the inverses of the two generators to the matrices shown. Now next, we consider a rather old result by Lipton and Zalkstein from 1977, in which they showed that if a group G has a faithful representation, then the word problem of G can be recognized in deterministic log space. As a motivating example, let's consider the word problem for F2, the rank 2 free group from the previous slide. The input to the word problem is a string, W1 through Wn, where each individual symbol, Wj, is either one of the two generators or one of their inverses. And the goal of the word problem is to determine if the product of this entire sequence of group elements is equal to the identity element. As Lipton and Zalkstein showed, this problem can be solved by a deterministic algorithm that requires only order log n space. And their algorithm works as follows. We make use of the faithful representation rho of the group F2 from the previous slide. By definition, rho of the input string W is equal to the identity matrix if and only if the input is in the word problem language, where here we're exploiting the fact that rho is faithful. And so all we need to do is check, does rho take the input to the identity matrix? The most obvious way to perform this check is simply to apply rho to each input symbol individually, obtaining this entire sequence of 2 by 2 matrices. We then compute the product of all n of these, obtaining some new 2 by 2 matrix, and we check, is that matrix equal to the identity matrix? Where here we're exploiting the fact that rho is a homomorphism. However, there's a problem with using this obvious idea in log space. Namely, the product of a sequence of matrices like this may be a matrix whose entries are very big numbers. And so instead, we're simply going to check, is the product of this sequence of matrices congruent to the identity matrix mod P for all small numbers P, where here congruent mod P is meant element-wise. The correctness of this algorithm follows immediately from the Chinese remainder theorem, and the fact that this algorithm only uses order log n space follows from a standard bound on the density of prime numbers. And so we have a deterministic log space algorithm that recognizes the word problem for the group F2. But of course, there's nothing about this idea that's actually specialized to group F2. And in fact, a similar idea works for any group that has a faithful representation. In other words, for any linear group. However, to be absolutely clear, the claim here is not that in log space, it's possible to carry out a calculation like this using an arbitrary faithful representation of a group. Instead, the claim is that if a group G is a linear group, then G has some carefully chosen, nice, faithful representation for which it's actually possible to carry out a calculation like this in log space, thereby enabling the word problem of G to be recognized in log space. Now, I emphasize this point because our 2QCFA algorithm for the word problem operates in a manner that's very similar to the Lipton-Zalcstein algorithm. However, the constraints of quantum computation will force us to modify what we mean by a nice, faithful representation of a group. In particular, we show that if a group G has a faithful algebraic unitary representation, then the word problem of G can be recognized by a 2QCFA. In order to show this, we first observe that faithful unitary representations are nice for 2QCFA, where a unitary representation of group G is just a special case of an ordinary representation. It's a group homomorphism from G into a group of unitary matrices. Representations of this form are nice for 2QCFA fundamentally because the basic computational step of a 2QCFA involves applying a unitary transformation to its quantum register. This observation by itself already almost implies that a 2QCFA can use a faithful unitary representation, rho, of a group G to recognize the word problem of G, using essentially the Lipton-Zalcstein algorithm. In particular, on input a string W1 through Wn, the 2QCFA will first initialize its quantum register to a carefully chosen state, and then simply apply the sequence of unitary transformations, rho of W1 through rho of Wn, one after another to the quantum register. As rho is a homomorphism, this has the effect of applying rho of the entire input string W to the quantum register. We can then check if rho of W is equal to the identity matrix by performing a carefully chosen quantum measurement. Except there's one problem with this approach. Namely, it could be the case that rho of W differs from the identity matrix, but is close to the identity matrix. If this happens, then it'll be very difficult to test if rho of W is equal to the identity matrix using a quantum measurement. So this is a problem, and to deal with this problem, we next suppose that rho is more strongly a faithful algebraic unitary representation, where now we've added the additional constraint that this is a representation into a group of unitary matrices with algebraic number entries. Representations of this form are very nice for 2QCFA, as the previous issue simply disappears. That is to say, now, if rho of W differs from the identity matrix, we're guaranteed that rho of W is far away from the identity matrix, where the distance is defined in terms of some function t. Now, a 2QCFA really can check if rho of W is equal to the identity matrix, with bounded error, in time roughly t of n. Therefore, if a group G has a faithful algebraic unitary representation, then the word problem of G is recognized by a 2QCFA. Naturally, the question then is, which groups have representations of this form or of a similar form that can be exploited by a 2QCFA? The main technical content of this paper is devoted to answering that question. We also note that, as an easy corollary of our result, we obtain a 2QCFA that recognizes the language LEQ, which is more efficient than the original construction of Urbanus and Watrous. We also note that the 2QCFA that we've constructed in this paper for recognizing group word problems have essentially optimal running time bounds, due to the lower bounds found in the companion paper. Lastly, we mention a few open problems related to our work. What is the exact classification of those group word problems recognizable by a 2QCFA in polynomial time? We know that if G is virtually abelian, then the word problem of G is recognizable in polynomial time. And in the other direction, We know if the word problem of G is recognizable in polynomial time, then G is virtually nilpotent. Can this gap be closed? Similarly, one could ask for an exact classification of those word problems recognizable in other time bounds, sub-exponential time, and so on.